So let's start. Thank you for being here. I hope you have enjoyed your weekend. And so now we are back about the subdoppler cooling mechanisms. And so we just write the total field in this configuration where we have two fields with orthogonal polarization that goes in opposite directions. And in fact, we have found that the total field was just something. So this is the EL square root of 2 divided by 2 exponential E omega L T cosine kz E plus I sine kz E minus plus cc. So this was the field, in fact, was changing polarization. In 0 we have a sigma plus polarized light. In pi over 2 it becomes sigma minus polarized light, and then again in pi it becomes sigma plus, and in between it is linear at 45 degrees and then linear at minus 45 degrees with respect to the xy axis. So now we have also, I just draw here, we have different Clebsch-Gordon coefficients for the sigma plus transition starting from the plus 1/2 level, and for the sigma plus transition starting from the minus 1/2 level, and vice versa. We have also a stronger coupling for the sigma minus level from the minus 1/2 level, and a sigma and a lower coupling. So this gradient of polarization will lead to a gradient in the light shifts. So now we will compute the light shifts only in the ground state. In fact, if delta is large with respect to gamma, then the atom spends most of its time in the ground state and very seldom goes to the upper state. And so we just can forget, so obviously also low saturation. The saturation parameter has also to be small. And so we can almost forget the excited state, just taking into account what occurs in the ground state. So the coupling we have seen, the sigma plus acts on these transitions and the sigma minus acts on this transition. And so to know the effect of the total field, we just have to sum up the effects of each polarization, because we have here, in fact, we have two independent. This is just one system which is isolated from the other one, and so we have two so-called V systems. And so it is rather simple to calculate. And so for this, we just call U plus of Z the light shift for this level, and in the low saturation limit with detuning much larger than the natural line width, it becomes simply omega 1 squared, and it is the cosine. So this transition acts with the weight 1, and we have 1/3 of the intensity for the sigma minus, which acts on this transition, and in this case you have the 1/3, which is the square of the Clebsch-Gordon coefficient. And obviously, for the -1/2 level, you will have the same thing, except that the 1/3 is here now. So obviously, you can play a little bit with this, and if you want, you can write this quantity as 1/3 plus 2/3 of cos squared kz. Keep in mind that delta is negative, so this is a potential that goes down, and so if you plot the potential, you will have so I will try to not to say stupid things. So more or less so this is so this is to the mean value. No, yes, no. So cosine is 1, so this is -1. Minus, we will say minus u naught, and here it is 1/3 of u naught. U naught being just h bar divided by 2 delta omega 1 squared. Okay, so just one remark. If we have, instead of this simple 3 levels, so in fact we have 2 V systems. If we go to higher Jx, for instance, the next one is the 1 to 2 transition, in which case you have one more level in the upper and one more. So for the central part, you have just the same, the coupling between this level and these 2 levels. But for the other part, you have a W system. And so if you just forget that here, if you split here, it is easy to calculate. And then you would have, so one level which doesn't move, and the 2 other that just goes around like that. But here it is the same level that plays a role, and so when you are degenerate, you have here an intercrossing, and you have an adiabatic coupling between the 2 parts, and you end up with something like that. No, the third one is here. This one is flat because you just have you add a cosine and you have a V system with the same Clebsch-Gordon coefficient. So you have cos squared plus sine squared, which is 1. So and the Clebsch obviously. And so the idea is almost the same. You have one lower level and one excited level. So probably it is less. It is the deep is larger somewhere here. Okay, so this was just a remark. We will not use that. So you can make all the calculation, the same calculation for this system, but we will not do that. Okay. Yes? No, because in the 2V system you have two independent systems. And so this is, you do not have the coupling. Here you have a coupling between this level and this level due to these two photons. And this gives you this anti-crossing of the two curves. Okay, the next ingredient. So here we have just considered only the dipolar effect. And so this potential, the force that derives from this potential can be viewed as a redistribution of photons from one wave to the other. And the direction the photon prefer, the atom prefer to transfer photons depends on the relative phase of the two waves. And so if you are here, you have a force that goes this direction, which means that the atom in this state will prefer to absorb photons from this wave and emit stimulated photons in this wave. Up to now, we do not have any spontaneous emission. So this is just absorption and stimulated emission effect. So now we just add the spontaneous emission effect, and we treat it as optical pumping. If your atom is just here and is sitting in a place where the light is sigma plus, so it is excited to this level, and from this level it has nothing else to do than going down again to this ground level. So if your atom is in a plus 1/2 sublevel in the presence of sigma plus polarization, it can do nothing else than staying in this level. If it is now in the minus 1/2 level in the presence of a sigma plus light, then when he arrives in the plus 1/2 excited level, he can emit a pi photon or a sigma minus photon. So this one is not interesting because it brings you back in your minus 1/2 level. But this one is very interesting because it means that after a few absorption emission, if your atom was initially in the minus 1/2 level, it will be transferred to the plus 1/2 level where it stays. So sigma plus light means all the atoms in the plus 1/2 level after a few optical pumping cycles. Obviously, the conclusion will be exactly reversed if you go to sigma minus. In fact, at this point, you just swap the role of the two levels, and the atom goes into the minus 1/2 level. So in fact, you have a strong coupling between the light shift and the natural population for the levels. And now if you move with an atom, so just consider that it is here at the beginning so this is the sigma plus position, this is the sigma minus, and so this is the plus 1/2 level. So your atom sits here with a velocity. So it will climb the hill, and when it arrives somewhere here near the top of this, it is in a place where it is in the plus 1/2 level in the presence of sigma minus light, And so I don't know exactly where, but somewhere here, the atom will undergo an optical pumping cycles that brings it here, near the bottom of the next well. And so if the velocity is enough, then it will climb again, and here it will undergo another optical pumping cycle, and so on. And in fact, what you see is that for each half cycles, that your atom has to go up, so it converts its kinetic energy into potential energy, and when it is here, it has an optical pumping cycle, and then the internal energy is dissipated into the photon, because here you see the spontaneous photon has a frequency, an energy, which is larger than the absorbed photon because of this difference. So the coupling, the correlation, let's say, between optical pumping and light shifts dissipates the kinetic energy. And so this will go on until the atom has not enough energy to reach the next maximum. And at that point, let's say it's arrives here, and then it goes down, and it oscillates back and forth in the bottom of this well. So obviously you can calculate everything, and for instance, you can calculate the probability to move from the -1/2 level to the +1 level, and you make all the calculation, and you find it is 2/3 of gamma, and you have 1/3 of omega 1 squared divided by 2 divided by delta squared plus gamma squared divided by 4, and you have your cos squared z, and you can guess that to go from the plus to the minus level, it is just the same thing, except that here you have the sine square kz. And as we are, so this you can recognize if you remember something of your previous lecture. This quantity is nothing but S divided by 2, which is the population in the upper level, which is supposed to be very small. Sometimes we can call this the quantity, so it is 2 divided by 9 gamma S. It is often called a gamma prime, which is or a small gamma, which is in fact the width of the ground level due to the coupling with the upper level. In fact, in the dressed atom approach, you know that the levels are not anymore pure levels, but they are a mixture of the excited and the ground level. And if you just give gamma as a width to the upper level, then gamma S is the part of the excited level that comes into the lower mixture. So now you just make the usual trick, and you write that the force is minus the gradient of the potential, and the total force is just simply the pi plus times the force F plus the pi minus the force F minus. And this are just the population in the two ground sublevels, and they are just coupled with an equation, the usual one, where you say that the population in the plus level, for instance, decays with the probability to go from the plus to the minus level, so you lose some population, but obviously you gain the population that comes from the other level. So these are simple rate equations, and you can solve them. So you can write the population of the two levels, and obviously if the atom moves, you also have to take this into account, and you end up with a force which is just alpha v divided by 1 plus v squared divided by a capture velocity. And you can compute everything, obviously, and you have 3 h bar k squared delta divided by gamma, probably with a minus sign because you want alpha to be positive, because you put an alpha here, and the capture range is just given by this gamma prime divided by 2. So now you have the friction coefficient that now increases with delta, but you have also the capture range that decreases with the detuning. So it is not so obvious to know what at the end you will have. But if you compare with the Doppler cooling, in fact, in the case of the Doppler cooling, we had a Doppler coefficient which was 2s0 h bar k squared delta gamma divided by delta squared plus gamma squared divided by 4, and but you have a capture range which was simply so k, which was simply delta or gamma, depending on which one was the smallest. And if you just, yes, maybe I can do that here. If you just compute alpha d divided by the Sisyphus, so yes, I will just put, you find out that it is s gamma squared divided by delta 2 plus gamma squared divided by 4, which is much smaller than 1. So it means that the friction coefficient for the Sisyphus cooling is much higher, more efficient. But you have also the capture for the Doppler divided by the capture velocity for the Sisyphus cooling, which is just on the order of 1 divided by s. So the friction is much higher, but the capture range is much smaller. And so if you just draw the force as a function of the velocity, for instance, you have the Doppler cooling. So it is the difference between two Lorentzians, but it looks like a dispersion. And on top of that, you have the Sisyphus cooling, which is much narrower and much steeper, but without being much higher. Okay, so now if we want to continue, we have, in principle, we have all we need. Yes, I think. So I write it, but I will not do it. So I will just say a few words about it. So here, in fact, we have obtained the equivalent of the mean force that we compute in the case of the Doppler cooling. So this is what we have obtained. If we want to do things properly, we have to now calculate a diffusion coefficient which is due to the Sisyphus, and make some calculation, and then we end up with the KB T Sisyphus, which is now this diffusion coefficient divided by alpha S, where alpha S is the friction coefficient that we have calculated. And if you make all the calculation, then you find that this is on the order of U0 divided by 5, or depends what is my U0. I'm not sure it is the same U0 that as here. But anyhow, you can demonstrate properly that you end up with an atom that will oscillate somewhere in this potential, and so with an average energy that sits somewhere in between, and so this is U0, and so I'm not sure of this 4, but it is on this order. Okay. What is next? So to make the connection with Helen's lecture, I would say that in fact here we are close to the resonance. We are in dissipative optical lattices. And the difference, so the main difference with the lattices presented by Helen is that here we have the coupling with the upper state that makes you emit spontaneous photons. But another difference is that usually our dissipative lattices can be very, very deep. You remember Helen just gives you her V naught goes up to 32 recoil energy. So this is the maximum value that is achieved for off-resonance, far off-resonance optical lattices. We are usually dealing with, so easily, with 1,000 E recoil, because we are much closer from the resonance, and even with low power in the waves, we can have deep. And just to put some figures on it, if you consider the atom I prefer, which is cesium, usually we can use dissipative optical lattices with a detuning which is on the order of 6 gamma or 10 gamma, and with intensities that are on the range of 10 milliwatts per square centimeters. And if you just use the same atom, But instead of using laser diodes, you just want to use a CO2 laser. So lambda CO2, I suppose you know it, it is 10 microns. And it means that, so obviously you are not allowed to make the two-level approximation and so on, but it doesn't matter for our purpose. The detuning for CO2 laser, you just have 5 orders of magnitude. In fact, you go from the range of megahertz to hundreds of terahertz, so it is 5 orders of magnitude. And as you increase the wavelength, you also lose 2 orders of magnitude on the recoil energy, because the recoil energy is k squared. So, and so it means that if you want to have the same depth as R 1000 ER, you just need a laser with a power of about 1 kilowatts per centimeter squared. So it is not impossible. You know, CO2 laser, you just have 1 kilowatt of output power, but you have to focus it a little bit, and so it is more difficult. So this was just an aparté, and so this with this kind of depth, then you can say that the harmonic approximation is good. And you have the oscillation frequency, which is 2 square root of U naught in recoil. And if you just go on, so you have your potential well. So in fact, it is a sine square or cosine square, but you just forget it. It is just an harmonic potential. So you have your vibrational levels, and you can compute also the transfer, the rate equation for the population of these levels, and you find that you have more atoms here than here, and almost no one there. In fact, they are more spread, and you can probe that with pump probe spectroscopy. So if you just now switch a pump laser with a frequency omega L laser, and you sweep a laser with another frequency, a probe laser with a frequency omega P, then you will see the stimulated Raman transition from this level to this level, and with a resonance when omega P minus omega L, no, sorry, the contrary. So omega L minus omega P is equal to omega oscillation. And in this case, you will observe a gain on the probe for this condition. And if you have the opposite, it means that you will absorb a probe photon to emit, if omega P is larger, then the major process will be absorption of probe photon and stimulated emission of a laser photon in the field, and so you will have absorption. And this was my first experiments on optical lattices, and this was the first signature of atoms localized in an optical lattice. Okay. Yes, but this we had some approximation. We have made some approximation at the beginning, which were that um, so yes, this is a yes. Here you have also the fluctuation, the fluctuation force. Uh, yes, but it makes no sense. You not equal 0. It makes no sense because you have nothing. Probably this approximation is valid only if you have oscillation trapped levels. So it means that you should have U naught larger than recoil. Otherwise, your potential is too shallow and you will not keep atoms in it. So the temperature, the Sisyphus cooling will not be efficient. Yes, yes. The recoil. This is sub-Doppler, but it is not sub-recoil. If you want to have sub-recoil mechanisms, then you have to play some other tricks. You can do that. I can explain it to you, but I think it will make me a bit late. The saturation intensity, IS, is 1. For cesium is 1.1 milliwatt per square centimeter. So this is the usual case where you are just playing. You say the saturation is low, but it is in fact 1/2 or one. So we make all the calculation assuming that the saturation parameter is small, but it is never so small. Here it is 1/3 or something like that. So this is, you divide 10 divided by 6 squared. So yes. Maybe one thing that, yes, I will say that because it is one point that Hélène mentioned, but I think it was not, she did not emphasize it. In fact, if you want to, so this is, if you go to higher dimensions, in fact, so this was a 1D, we had 2 beams, and what is important is to notice that the basis of the reciprocal lattice is the difference in the k vectors that you are using. So in 1D it is simple, you just have 2 wave vectors, k and minus k, and the base of the reciprocal lattice is just minus 2k or minus 2k, doesn't matter, and it gives you a spacing of lambda divided by 2. If you go to 2D, it is better to use only 3 beams, and in 3D you just use 4 beams if you do not want to have some troubles. So this is very easy to demonstrate. You just write your total field, which depends on R, as the sum of E, kj, R, with j equal from 1 goes to 1 to n, and you play a little bit. You just decide that n is somehow special, and you write it as j equal 1 to n minus 1 exponential I kj minus k n r plus 1, and you have a global phase which is I, K, N, R. It's just playing a trick. And this shows that if you make a translation R that conserves this phase, then, which is the definition of the lattice, then it shows that this is just what Hélène calls the Bay-J, the vector of the reciprocal lattice. So in the case that she has, if you use two standing waves, in 2D, then you are in a pathological case where you have more than 3 beams, because you have 4, but you are in a sense lucky, because if you just draw your 4 wave vectors, so this is, let's say, K1, K2, K3, K4, and you can construct the differences just like that. So these are B1 and B2, or vice versa, I don't know. And you have, if you also write B3, the third one you can construct, it turns out to be just the sum of B1 plus B2, because the K1 and K2 are opposite, and so this is just minus 2K4, which is also equal to K3 minus K4, because, sorry. So in this case, in fact, you have your differences in wave vectors are redundant. One difference is just a linear combination of the two others. But you have to be careful when you choose the one you want to use as a basis. And it is always a good idea to choose the shortest ones. And also the simplest. And you remember when Hélène introduced the phase difference between the standing wave, and she said that in this case you have no interference. And she had a square lattice with a period which was lambda divided by 2 in each direction. And then she shows you the case where phi equals 0, and in this case you add what she mentioned as so it is also a square lattice, but with the periods here at 45 degrees. So in fact, in reality, it is not a sudden change in the Bravais structure when you go from 0 to pi divided by 2, because here you have the impression that your periodic lattice is here, and which is different from that. But you just change the phase of your lasers. Why did you change the deep nature of your lattice? In fact, it is not true. This is not the good lattice. The good one is always the same. It is this one, which is the same. But you have a kind of decorated first Brillouin zone, which means that for any phi, you always have 2 sites, 2 wells, in the first Brillouin zone. What happens is that in this case, the second potential wells has, for phi equals 0, a depth equal to 0. So it is a pathology, it disappears. And the other case here, in fact, the two wells with the same depth. So these phases do not change the nature of the Bravais lattice. You have always the same wave vectors, and but you have, as in salt, if you just take NaCl, you have one site for the sodium and one site for the chlorine in a single Brugger zone. And so here you have almost the same. Okay. Question? Yes, yes. In fact, it is just that you have, if you just look at the two standing waves, in one direction you have a plus, minus, so it is always antinode, but they have opposite signs. So in this direction and in this direction you just have, so here it is clearer, plus, minus, and you have a standing wave in the other direction, which is plus, minus, and what you have to sum is the field and not the intensities, because they are in phase. So plus, which gives a maximum of intensity, but here you have plus, minus, which gives you 0. And here you have again plus, you have a site. And here you have minus, which gives you 0. And minus, which gives you a site. If now you have a phase between them, which is neither 0 nor pi over 2, then it will depend. If you have a plus, it will always give you a higher value than if you have a plus minus. And so you will have a site here and a site there, but this one being deeper than this one. In fact, with the pi over 2, the two standing waves are in quadrature. You know, a standing wave has the same phase everywhere. It can just eventually change sign. And if they are in quadrature, they remain in quadrature if they are plus minus or minus plus. Because so you have, I don't know, the notation is Ex plus or minus Ey, yes, X and Y for the standing wave like that and the standing wave like that. And doesn't matter if you have plus or minus, if you just take the squared value of that, it is just E plus squared plus Ex plus Ey squared. So this is just the phi equal pi over 2. Otherwise you have here a cosine to cosine phi, and this plays the trick. Okay. I am a bit late, but not too much. Okay, let's start the last part of my lecture, which is beyond the standard mod. So we go back to Doppler cooling. In fact, we know that Doppler cooling is important at small detuning. So typically for the optimum value for the Doppler cooling is on the order of minus gamma divided by 2 or something like that. And also if you are working with high intensities, so relatively high intensities, because you always want to be non-saturating, because if you saturate, you know. So you can do the experiment in the saturation situation, but you cannot make the theory. And so, but if, so when the detuning is small and the intensity is relatively large, then the Doppler cooling is more important than the sub-Doppler cooling. You have almost a Doppler temperature and so on. So now we just look at the spring constant and the size of the mott. You remember that we had, in fact, the force that we have computed was minus alpha v and minus kappa r, where we have here this spring constant, and with the value, ugly value, which was minus delta gamma omega 1 squared divided by delta squared. And so this is just the usual term, and KL, and then you have your G mu B divided by H bar, where B is the gradient of the magnetic field. So if you just, so you forget that, because now you go, let's say, to low temperature, and so you just are interested in the space component, and you say that as you have a spring constant, you have a position spread, so in 1D, which is just a KBT. You know, you just have restoring force, but you have some agitation, thermal agitation, and so you can escape and go a bit further. And so this is the spread of in position. And this, I recall, if you just go to the minimum temperature, it is just gamma divided by 2. H bar, obviously, to have an energy. And if you put some figures in that, so the typical figures are a gradient of 10 Gauss per centimeters. Mu BB, everybody knows that. So mu BB divided by H bar. No? Okay, it is 1 megahertz per Gauss. And so you put everything in it, and you just find out that you expect a spread. So I hope I did not make mistake, which is 0.5 10 to the minus 9 meters squared, which means that you expect a delta X on the order of 20 or 25 micrometers. And this is much less than the observed values, which are typically on the order of 1 millimeters. So obviously you can argue that here I have maybe a factor of 10, but it is only the square root of 10 that will play a role. And so in the worst case, I will have 100 micron instead of 1 millimeter. So it's one order of magnitude is missing somewhere. And also, one important thing is that in this calculation, this is independent of the number of atoms. And if you have seen a MOT working, then you notice then as you add some atoms in the MOT, it becomes fatter and fatter. So clearly we miss something. Maybe we are wrong by a factor of 10 in K, but it changed only a factor of 3 in the spread. But the important thing is that we have forgot something, and obviously what we have forgotten is just the fact that we have more than one atom. Up to now, all the calculations I have made are just for one atom. I have one atom interacting with the field, and I make some mean values about that atom, but it is only alone. So, point 2 is what are the role of the other atoms in the cloud. So, we have a cloud with some atoms, and I am interested in one specific atom. So this is my atom, the one I am interested in. It is somewhere here. So, what do I have? I have some light coming from this direction, and I have some light, no, not this color because it's the same, sorry. And we have some light coming from this direction. And all these guys in the cloud will absorb some light, which means that here we have the intensity I minus, and here I have the intensity I plus. Outside of the cloud, so at the infinite, plus or minus, they have the same intensity. But to reach this, my atom, the intensity of I plus has to go through all this huge amount of atoms, while I minus just have to go through a small part. So I have to take into account, so the absorption of the laser beams. So I will just write that the I plus divided by the x, so this is, I will restrict to one dimension, so this is x, is just, it goes down with the number, the density of atoms in x, a cross section, an absorption cross section, which I call sigma L because it is for the laser light, and it is proportional to I plus of x. If I write the same equation for I minus, I just have the plus k sigma L A minus, because the A minus, the I minus is propagating backwards, so its intensity increases with x. In fact, it decreases with propagation, but increases with x. So the Doppler force was the sum of F plus F minus, and in the calculation I have already made, I have assumed that the two intensities were the same. And you remember we made the calculation with something that was with a detuning, which was delta plus, no, minus plus delta plus squared, gamma squared divided by 2, and here it was plus minus squared. So something is missing, but it doesn't matter. And what we have said is that we're working in this with the same intensity, and we just make the expansion with delta, which was the small parameter, the velocity, plus the j mu b divided by h bar. And we just end up with something which was alpha divided by k delta. But if now the two intensities are different, then we have an extra force, which is the difference in the total. We have obviously the same alpha v minus kr that comes from this development, but you also have something which is yes, no, h bar kl divided by delta. So, and now we have a force that depends on the difference in intensity. And if we come back to this drawing, we see that here the I plus is lower than the I minus because it has more absorption, it has experienced more absorption, which means that the resulting force, so this part of the force, the I minus intensity is higher, so it pushes stronger, and so you have a compression force. And so it's bad, because a compression force is something that tends to reduce furthermore the size of the cloud, and we observe clouds that are too fat, and so obviously this force has to be taken into account, but it is not the component that will explain the fact that the trap is is larger than what is expected. So this is called the shadow effect. This is a shadow force, if you want. But it is not the one we are interested in. So, what next? In fact, we have considered the role of the absorption of the laser beam by the other atoms, but we did not take into account the fact that the other atoms will emit spontaneous So, in fact, it is what we call the multiple scattering. And so it means that in your cloud, you can have here an atom that absorbs a photon from the wave, from the laser, or from anywhere else, and it will emit a spontaneous photon in some direction. And just by chance, my atom, so this, let's call this atom A, and my atom, which is B, which is sitting here, is just exactly on the trajectory, between quotes, of this photon, and it will absorb it. So initially, we have A in the excited state, and it emits a photon with K spontaneous, this one. And so it means that A has a recoil which is minus H bar K spontaneous. So, to emit this photon, my atom A has to minus H bar K spontaneous. And then my atom B absorb this K spontaneous. So it ends up in the excited state. And now B has a recoil which is plus H bar K spontaneous. So it means that in this process you have a kick given from atom A to atom B, which is the same as the result of a repulsive force between the two atoms. So if you look at the probability of this process, in fact, your atom A has to emit the photon in the good direction so that it can be absorbed. So to be absorbed, it means that the direction of your beam should be something that is a cross section divided by the square of this distance. In fact, this is the probability for this process to occur. Obviously, also with the density of atoms and so on. And so this sigma is the cross section for reabsorbing a spontaneous photon. So it is not, I put an index R, and sigma R is not sigma L, because the spontaneous photon emitted by A have a spectrum that is different from the spectrum from the laser. Typically, it is the mono triplet, which was on the poster, on your poster. And so you have a spread in the frequencies that are emitted by the photon. Your laser is just at omega L, but the spontaneous emitted photons have a spectrum that is known as the mono triplet, which has three, obviously it is centered on omega L, but it has a blue component and a red side component. And it turns out that this blue component is closer to the resonance than the laser. And so if you make So to make the calculation, it is rather tricky, because this absorption cross-section is the convolution of the emission spectrum of A and the absorption spectrum of B. So it takes some pages of calculation to compute it, but usually you end up with sigma R, which is larger than sigma L. And in fact, at this point, you can conclude that the repulsion is larger than the compression due to the shadow effect, and this repulsion will explain the size of the mode. Okay, let's continue. Point 3. In fact, okay, so now we have a, yes? Yes, but usually you do not go to the regime where the absorption is so high that you have nothing at the end. Because if you have nothing coming from this side at the end, then you will not trap anymore. So usually this model is valid in the not too high absorption coefficients. But yes, it is true that, so this is, but in fact, it is just the point I want to mention, is that if you, this is a problem, because, nonlinear problem, because the intensity depends on the density. The repulsive force depend also on the number of scatters that are present. And so you have some nonlinear equation everywhere, and when you have a nonlinear problem, you never know if it will go to a steady state, an equilibrium, or if it leads to some oscillation and instabilities. So for the instabilities, you have to go to the poster by Brice, who is here. We will present it tonight, so don't miss it. But let's start with a simple model at assuming that the temperature is 0. So the temperature is 0 means that you just forget that the atoms are moving and everything becomes, and you just write, you assume that you are able to find some equilibrium. So it means that for my atom, my favorite atom, I have a mod force plus the shadow effect. So this is the usual minus k r, and plus the multiple scattering force. And if it is equilibrium, just for every atom, it goes to 0. So this force is rather difficult to handle, but as you see that it is 1 over R2 force, it reminds you of the Coulomb force, and so you know that the divergence of the Coulomb force is just the density of charge. And so instead of considering this equation, you just consider the divergence of this equation, which obviously is always 0, but without the vector. And this kind of arguments leads to the fact that inside the cloud, the density is a constant. In fact, in the MOT, you just have minus kx, so the divergence of that is easy to compute. The shadow effect is the same. You have to take the difference in intensity, and the divergent of the difference in intensity is just here, so it is the density. And this is just also related to the density because it is a Coulomb force, so the divergence of the field of the force is just the density of the charge. And so it means that you have a field sphere, but it has nothing to do with the Fermi sphere. We have just classical atoms, which are boson or fermions, it doesn't matter. But we have a sphere with a radius r, which is depending on the number of atoms. As the density is constant, then you have a relation between the total number of atoms that are trapped and the radius of the cloud. Obviously, 4/3 of pi and so on, but it doesn't matter. So, and you observe something which is consistent with, so you expect something which is consistent with the observation, that is that the radius of the cloud increases with n, but it is rather difficult to check that the density inside the sphere is constant, because when you take an image of a field sphere, you have a larger depth in the center than on the edge, and so you still see an image like that. And so is it, you know, you should prefer to have the real image of a constant density with an image like that, but because it is a sphere, you have the depth of field that makes you something that looks like a Gaussian or anything you prefer. So it is difficult to check experimentally that the density inside the cloud is constant. And also, if you consider that the effect of the temperature, in fact, it is almost the same as the effect of the temperature when you have a field sphere. Inside the sphere, so the atoms move, but they are always inside the sphere, so the density inside the sphere is always 1. But the only difference is that at the edge, instead of having a sharp cut, you will have the effect of the temperature, which smoothly blur the border of the sphere. Yes, 10 minutes. Fantastic. Yes. So to demonstrate that, you just, instead of considering the sum of the force, you consider the divergence. And so this is just Kr. So the divergence of that is just simple, because so this is just K. This shadow effect is related to the difference in intensity plus minus. And so its derivative respect to x is just the derivatives of the intensity I plus and I minus. And it was written here. They were just proportional to the density and themselves. And the multiple scattering, it is just the analogy with the Coulomb force. So this is the fact that you have a force that is proportional to 1 over R2 and which is radial. It means that it is equivalent to charged particles. And you know that when you have a Coulomb repulsion problem, the gradient of the force, the divergence of the force is related to the density of the charges. And so this one is just a constant, and here you have it is proportional to the intensity. This one is proportional to the intensity. And if you are in the low absorption regime, so you can replace I plus of x by I plus at infinity. And so this is just k, and this is n times something. And so you end up with n equal constants. So obviously, yes, you have made some assumptions to arrive to n equal constant and low absorption and so on, but it is not so difficult. Okay. So this is the case of equilibrium, and very often people who are playing with their mod and changing the parameters just sometimes go to small detunings, so delta on the order or lower than gamma divided by 2, and they have a lot of atoms that are trapped, and suddenly they observe that the number of atoms trapped depends on T. If you have played with a large mod with a high number of atoms, you have observed it, and you just turn a knob to go to higher detunings and everything settled in a smooth way. But obviously you have to find why you have all the parameters of your mod which are constant, and suddenly your mod begins to breathe, to move, to shake, so this is always a bit surprising and obviously also interesting. So obviously if you just need the mod to prepare a BEC or something else afterwards, you just avoid this regime. But we are interested in the mod itself, and so we are looking at this regime. And to do that, we go to a phase space description of the problem. So we introduce the density of atom depending on the position, the momentum, and the time. And we play some tricks by separating artificially the contribution from the hot atoms, which is almost a flat background, and the cold atoms, which is expected to be something which is localized in P and in R, because this is because the friction force, and this one because of the restoring force. So we have, in fact, strictly speaking, we are interested only in the contribution, the space phase density for the cold part of the sample. And the background is just something flat at the scale of interest for us. So the first attempt is just to write a kinetic equation. You know that, so let's do it. So you just write d divided by dt, total derivative of rho, would depend on r, p, and t. So usually you write it as a partial derivative d dt of rho, r, p, and t. Yes, maybe I will switch to 1D. Yes, maybe it is simpler. So I switch to 1D, but it remains, it avoids to write some gradients in a strange way. So it becomes x and p without. And you know that you have also to take into account the fact that the atom moves, and in this case you have d over dx of rho of x, p, and t. And usually you write p dot and d over dt, dp of rho of x, p, and t. And so this is usually the force. So here we have to be careful, because this force depends on P, and in fact what you can show is that in this case you are not allowed to put it here, but you have to switch to move it here. So in fact it is not anymore the Boltzmann equation. So this is the usual Boltzmann equation. As the force is not independent on the velocity, you have to take it into the derivative. So at that point, when you write that, you obtain the Vlasov, the so-called Vlasov equation. Sorry. And obviously, what is missing is what is here, and which is the collisional terms, which are ugly. So for the moment, just forget it. So this is already nice, but one ingredient is missing here, is the fact that we have some random diffusion in momentum space. So if now, so we again have to take into account the spontaneous emission, which leads to a diffusion in momentum space. And to take that into account, we have to add in our Vlasov equation an extra term, which is known as a Fokker-Planck term, which is just has been found in a treatment of the Brownian motion, so it is not new, it's not really new. And so at the end, we have the simple equation, which is P over M d over dx of rho plus d over dp of the force times rho plus d2 and dp2, so the diffusion coefficient. And again, this is the collisional terms. So very often you can see that people consider that the diffusion coefficient is independent on P, and so they plugged it here instead of being there. But so this is usually an approximation, and putting it inside allows you to do more. And now, if we look at what we want to write as collisional terms, then there is an easy part, which can be interpreted as the collision between a cold atom and a hot background atom. If a hot atom just collide with a cold atom, it just kick it out of the cloud. And so you have a first term which is rather simple to write, which is just the density divided by a typical tau, which is the time, the collisional time with the background. There is another term that is rather easy to say, to write, and it describes the fact that sometimes two hot atoms collide and gives you a cold atom. Why not? It may happen. And so this gives you a source term, which I call lambda, and which can be assumed to be homogeneous in space and in momentum, because it is just a collision between two hot atoms that puts you an atom in the range of position and velocity you are interested in. And obviously then you have the usual double sum on all the possible incoming colliding pairs of cold atoms, which gives you some other pair of velocities, but we just drop it. We consider that everything concerning the cold atoms is governed by the magneto-optical trap, so the forces that are the optical forces. Here you have real collisions, so in the sense of Yoke lecture, where you have the collisional cross-section, which is orders of magnitude lower than the term that is mediated by light. So the light effect is much larger than the real collision between two atoms. Okay, so it looks simple, but as usual, here you have the force, and this force, and this coefficient, diffusion coefficient also, depends on the intensity I plus and minus, which depend on x, and they depend on rho elsewhere. And so you have, because obviously the n of x that was in the equation for, so ddx of I plus or minus minor or plus sigma L I plus or minus. This is nothing else than the sum over p of rho of x, p, and t. And so, in fact, you have, and also this now depends on the density, and so you have here some nonlinear dependence, and so you end up with non-linear coupled equation. So, in fact, it is integral, differential, and a partial. So I don't know what is the name of this kind of equation, but it is rather complicated to solve. And so I will not go further, and if you have question about this equation, you just ask Brice tonight, and he will explain everything. Okay, I am 5 minutes late, but not too bad. Any question? No? No? Yes? Yes, in fact, two hot atoms collide, but only one remains. The other one takes, yes. So it's not, yes. Yes. Yes, in the simple case, you have the density which is constant. If you make the experiment and you load a very large MOT with a large number of atoms and you go to small detunings, you will observe that your MOT is not stable anymore. And you want to explain it. So if you are just interested in a MOT as a tool to have cold atoms to make afterwards some evaporative cooling or something else, then you just turn the knob back to larger detuning where your MOT is stable, and then you make the experiment with your stable MOT. And you just forget that in some condition it can become unstable. If you are a strange guy like me and you are interested in non-linear dynamics and things like that, you say, okay, what are the key ingredients I need to describe this instability? Yes, this is so the Vlasov-Fokker-Planck equation. It is just an equation that appears in plasma physics or in high energy physics when you consider charges that just going around in a accelerator ring. You can write equations that are on this form also, except that the force here is deduced from the Coulomb repulsion. So it is the Poisson relation that gives you the force instead of the absorption due to the other atoms. So there are differences, but there are also some similarities. So I won't say that it is plasma physics, but in plasma physics they have to face the same kind of equations, so the same kind of problems, and so some connections are possible. Any other question? Okay, thank you. Coffee break.